And today I'm going to talk about gossip algorithms. These are algorithms for very large dynamic systems. And before I start, a few seconds of respect for the Ukrainians who are fighting for their freedom and for ours. Okay, I want to talk about gossip. I've got the course project. It has to do with crypto stuff, and random peer sampling is a part of that. I remember in the Delta QSD we also had a little bit of discussion on peer sampling or block diffusion, and so there's a whole lot of this kind of gossip related stuff going on in the crypto community. So you'll see a little bit of that during the project. And today I want to talk about gossip. Before starting, just a few things. The talk by Neil Davies from last Thursday, it seems like he's very talkative, he's discussing many things. It's actually a very dense talk. Everything he says, there's a lot of things behind it, and if you don't really understand the stuff, then it seems very straightforward, or maybe not, but there's in fact a lot of things going on there. And so he basically kind of gave you the tip of the iceberg. I will put a link to the video of his talk. I will give you that as soon as I get it from Siegfried Mason. And so it's worthwhile to look at the talk again. What he presented is just the tip of the iceberg, and all the things you saw in the two lectures before. All of that is part of what he said. So you see there's a lot of things going on there. And he told you some simple stories, but maybe it was not so clear how strong some of these stories were. So the small cells example that I showed is a real event. It really happened. And the delta Q is actually really very powerful technique that is not yet so well known. So I think it's probably worthwhile looking at the video again when you have looked at the slides in the last 2 weeks. And you'll see that there's a lot of more meaning in what he says. Okay, so today I want to talk about gossip. Gossip is a very general technique about making large algorithms for large systems. Gossip is used in many, many places. It's kind of a bootstrap. It's like the first step. What do you do if you have a random bunch of nodes and you want to impose something on them and do something? And that's where gossip comes in. It's scalable. It is extremely simple, you will see. And also the project, the Cyclone algorithm is not so complex, so which is a kind of gossip algorithm as well. It's also very robust. All kinds of failures, network partitions where networks are completely breaking, even many, many node failures, maybe 50% of the nodes crash or more, 80%, 90%, and it still works. Okay, so none of this majority stuff anymore. This is really an algorithm that works in extremely hostile cases, okay? And the idea is very simple. Gossip is, in French, bouche à oreille. It's nodes talking to each other, exchanging information, and recursively, and so the information propagates. So I know something. I'm sitting next to Ali. This is Ali Goksi, who finished his PhD a few years ago. I tell him something, so we know, and then Ali tells Kosmin, and I tell Talat, 2 more PhD students. Now we're 4 of us. This is known as a push epidemic. Okay, it starts with one person, then two, then four. Now, you can also have a pull epidemic, where the other person asks me for information, and the information is pulled out, and you can also have push-pull. I'm telling things, but information is also coming back to me. Okay? It's going in both directions. So you can see there's like 3 ways that the information can travel. Now, some very nice properties. Some very nice properties of this. Each node is doing fixed amount of work. Even if you have a huge system, millions of nodes, every node is still doing a fixed amount of work, independent of size. Also the network, the messages in the network, millions of nodes. The network load is scaling with the system size, linearly. So it's not getting more loaded. And the information spreads kind of like this. It starts, nobody knows. So this is percent infected, that's how many nodes. When you start doing gossip, it's growing exponentially, okay? See, this is exponential growth until you start getting close to the actual size. Then you have kind of a saturation effect where the increase slows down. This is a very general, this is known as an S curve. All exponential growth is actually an S curve. Huh? Everything that you think is exponential, you're only here. The economy is growing exponential. The number of mobile phones is growing exponential or whatever. What that means is you're here. Eventually, the number of mobile phones saturates. So this is true for everything. So here, this is for the gossip algorithm. Okay? So this is a general thing of large systems, this S curve. Okay? Okay, so what is a gossip protocol? We're going to make a kind of precise definition. You have a bunch of peers, so all the nodes are called peers. There's no central node. All the nodes are equivalent. They're all called peers. And each peer talks to another peer. So here I have P1, it picks somebody, random guy here, P5, and they sends a message and gets a reply. That's a pairwise interaction. Okay? But all of them do that. So P1 does that, P3 does that, P5 does it, P4, they all do the same. So all of a million nodes, every cycle, they make one interaction. Okay? Pairwise interaction. So each node does only a small amount of work. Okay? But they're all doing it. And every cycle. This is periodic. So the cycle can be long. Maybe it's 50 milliseconds or 10 milliseconds. But it's very long compared to the processor or something like that. It's very kind of long time. And they send messages. And the messages are small. So this small message here, there's a small amount of data stored here. Small amounts of data everywhere. So the state of each peer is bounded, typically small. The amount of data in the message is small. Okay? And then when the interaction happens, the state changes. Okay? You go from S to S prime. The state is some computation. And that's it. That's a very simple model, huh? You see that model? Each node picks another node. Every 50 milliseconds, sends a message, gets a reply. But all of the nodes are doing that. So you see, the information will propagate farther and farther. That's very simple, isn't it? It is very simple. And we'll see what we can do with that. Okay? So there's some assumptions. First of all, we do random peer selection by basically kind of random. It's not completely random usually, but it's some kind of a protocol, and it should be somehow random in some ways. Maybe each node knows all of the nodes. So if there's a small number of nodes, each node, P1, can know everybody. But in a big system, that's not possible. And anyway, the nodes are always changing. So there's no way a node can know all the nodes. So each node has a small set of neighbors. So P1 maybe just knows a few neighbors, and that's it. So he knows 4 nodes, and they can change all the time. These neighbors can change. Maybe the neighbors crash or something. So the neighbors are always changing, okay? Because nodes can leave or crash or come. It's completely dynamic. So you see, it's really different from the algorithms we saw in the first part of the course. So there's no fixed number of nodes, okay? And it's not small, it's huge. It can be millions, easily. And the communication is not reliable. Messages can drop. Maybe 10% of the messages are thrown away or slow. Okay? So this is a whole different way of looking at the algorithms, Also, we assume that the cost of the protocol is negligible. What that means is that when we have one cycle, like 50 milliseconds, the amount of computation or the round trip of the message is much smaller. So the frequency of interaction, the 50 millisecond, is much bigger than the message travel time or the computation. So the frequency of interaction, maybe it's 50 millisecond, 20 times per second. But the message round trip might be a fraction of a millisecond or microsecond for a small system. So it's very slow in a sense. So the load is actually very slow. Okay? So that's the idea of gossip. You can see it's a wholly different way of looking at things. The number of nodes is always changing, not fixed. And each node does a small amount of work periodically. So the cyclone algorithm, one in the project, is doing like that too. Okay. What can you do with this? You can do lots of stuff with these gossip algorithms, and they're used a lot. One thing to do is dissemination. Like a broadcast. You know broadcast or multicast. Reliable broadcast. Reliable broadcast is good when you have a small fixed number of nodes. Like U.S. Army talking to a small number of missile silos for a uniform reliable broadcast. But here we're talking about millions of nodes. And we want to spread information around. Okay? So the information is traveling. So you see, it's much weaker than reliable. It's not like all or one or something. But you know the information will eventually get there. We're still in the eventual world, but it's a different kind of eventual because it's based on this diffusion idea, okay? So this is called event dissemination, or you have background data dissemination. So lots of systems, even the computers you have, they are doing gossip. So Windows or Mac OS, those machines, you have this thing called iCloud or whatever. It's doing a lot of stuff in the background, okay, that you don't know about. Information is flowing, and it's in the background. So it's like this information flowing, okay? So that's one thing. Another thing is repairing. Fixing systems. So this is another application of gossip. This is called anti-entropy. And because gossip is extremely robust, when everything breaks, the gossip will still work. Okay? And for example, let's say I have replicated data. I have replicated database, 2 or 3 copies, like the shared data I have. And actually, I didn't mention it during the shared data, but a lot of those systems use anti-entropy. And it's gossip. And basically, the nodes are replicas. And they say, I have such and such data. And this one says, I have something. And they can see that it's not the same. So maybe the data is a little bit broken here on P5. Because you can usually detect when it's broken. Then it gets a fix from P1. So as long as there's one node or a couple of nodes that still have good data, then the anti-entropy will fix things. You compare the replicas, you reconcile the difference. So you can see in the background of many very fast, sophisticated algorithms, like the shared data we saw with N algorithm. There's usually an anti-entropy in the background. All the big cloud databases do anti-entropy, okay? It's fixing things slowly. So things are always degrading over time. Maybe this gets corrupted or something. So it's like slow degrading. And the anti-entropy will fix that. Okay? So the trick is, if we aren't in a hurry. Gossip is like the slow but sure way. It will never break, and it will always bring things kind of back into order. Okay? And then one example is what's called bimodal multicast. This one uses just best effort. But if some nodes don't get, we don't know that, huh? Maybe some nodes, the new nodes coming in, or maybe there's a network problem, and I do best effort, and let's say the source is not crashing, huh? I'm sending to everybody, but some nodes don't get the answer, but they're always gossiping. So P1 says, I got it, P5 says, I didn't get it, and P1 says, oh, here it is. So gossip fills the gaps. So gossip is the way to fix lots of problems, okay? And more examples, membership. I have a group of nodes that are in some kind of a social network or something. I want to join, or I'm doing some kind of a peer-to-peer file sharing, and I want to join BitTorrent, which maybe we see later. I want to join the group. So gossip will do that. It starts with bootstrap. So there's a website, for example, that has a small set of nodes that you know are in the group. Okay? That also can change, but there's some small set, like 10 or something. But the actual group has maybe 10,000 nodes. So you go to the website, you pick one of these nodes, and then you gossip with it. You ask that node, tell me some more. And the node tells you, here's some more, and you keep gossiping, and eventually you have a random set of neighbors, and you're part of the group. Okay? Processes I've heard from recently. So if I get a message from a process, that means I know that one. And if that node has message, then it will tell me. So the information about the group is disseminating. And each node will have some random set of neighbors, but all together they're like a group. So there's connectivity. If I have a million nodes here in this random set, just draw a few of them, and I want to talk between this one is part of the group and this one is part of the group, but they don't know each other. But this one knows another one, and this one has another neighbor. So eventually, the information disseminates, okay? And it's always changing. The information is never constant. The set of neighbors is always changing because, and this is called churn. In French you can say brassage, l'ensemble de brasser. It means that it's like a big mixture, and new nodes are coming in, old nodes are filling, so it's always changing. So the neighbors are always gossiping, so the set of neighbors is always changing. Nothing is constant. Okay? Okay, another application of gossip is doing computations, aggregates. Okay? Let's say I want to find the average, or the total amount of memory in the system. All the nodes have some memory, and if you add it all up, you get some total. Or I want to know the average computational load of all the nodes. Or I want to know the number of nodes in the system. Nobody knows how many nodes there are, right? It's totally different from what we saw before, right? There can be changing numbers, or the number can be sort of constant. If you have churn, maybe every 5 minutes, 5% of the nodes are leaving, and new nodes are coming in, 5%. So the number of nodes is approximately constant. This is an aggregate. How do you compute the number of nodes in such a system? It's very different than the fixed systems we had before. How do you do that? You use gossip, of course. I'll show you how to do that in a little while. Also, more important kinds of algorithms, network topology. Let's say I have a bunch of random nodes, and I want to organize them. I have a bunch of random nodes, like here, a bunch of random nodes, and I want to organize them into some structure. Let's say I want to organize them into a cube, so that each node, here for example, each node has 3 neighbors, and they form a cube. But I don't have a cube, okay? I have 8 random nodes. But I need a cube, or I need a ring. I have a bunch of nodes. I want to organize them as a ring, or in some other structure, or a torus. You can use gossip to do that. So gossip is like the bootstrap. Starting from randomness, you create order, okay? Starting from local view of fixed size in a random network, you do gossip, and each time you exchange information, you try to improve the structure. So if this guy, for example, if it finds out, it wants to know that what are these 3? These are the 3 neighbors. These are 3. So when it finds these guys through gossip, it figures out these are my neighbors. And this guy also needs to have 3 neighbors. So there's some kind of an optimization number, the approximation that you try to improve. And gossip is like converging to that. You keep the peers that are somehow close to you in the topology, and you throw out the others. So starting with random peers, you slowly converge to something which is ordered. Okay? That's something that gossip is really good for. Starting from randomness, create order. Anti-entropy also. Random breaks, fix them. Okay? Gossip is really good to combine with what we know before. Let's say we have some kind of a broadcast or some kind of an algorithm that's very fast, but it's fragile. So here I have what's called a spanning tree. So I have a bunch of nodes, and I connect them all. It's connected, but there's no cycles. So that structure is called a spanning tree, and I can use it to do broadcast. The algorithm that we saw in the paradox of time complexity, it basically creates a spanning tree when it executes. So the nodes, so the parent nodes are the ones that are somehow closest. So it kind of automatically creates a spanning tree. And if I do a broadcast from here, I just have to send it across these nodes, and eventually everybody gets it. So that works well. It's very fast. If I have n nodes, it's only n-1 messages. But it's not robust. If one of these links crashes, the algorithm breaks. Oh, so it's efficient but fragile. But gossip is exactly the opposite. It's resilient but slow. Each node has neighbors, and it's always changing. So if nodes crash, it doesn't matter, because you have other neighbors that are not crashing, and the crashed neighbors will be replaced by other neighbors. So the gossip algorithm is always repairing the connectivity, and so you can combine the two. If this spanning tree breaks, you flip to gossip, and the gossip is used to repair the spanning tree. You find a new connection between them using the gossip. Okay, and this is a real algorithm. This is called plum tree algorithm, which is used in cloud databases. Because in cloud databases, the nodes will crash, and you don't want the database to crash. And the connectivity is guaranteed by gossip. And the efficiency is guaranteed by spanning tree. And the combination is like a sweet spot. Huh? You get both efficiency and resilience. You see, so this is actually a very different way of making algorithms than we saw in the first half of the course. The gossip is a really good helper. Okay? So that's some of the ideas for gossip. And there's more things. Failure detection, clock synchronization. I'll show an example later. Certain kinds of reputation dissemination, other kinds of things. It's used in crypto blockchain algorithms. So there's many things. So the trick is, it's always the thing that crashes last. Gossip is always the algorithm that keeps working when everything else is broken. So it can build up the system again when it's very broken. Okay? And it's slow but very resilient. Okay? Let me now look at a very precise thing. And we are going to, actually it's interesting because it's connected to diseases and COVID and stuff. Because gossip is like contamination, information dissemination. And we'll put some numbers on it. We'll try to be a little bit more precise. So you have a peer here, and it wants to disseminate a message. Okay, so the peer has an amount of memory, buffer B. Okay, and it does a certain number of hops. Not infinite number, so the message is sent a certain number of hops to a neighbor. Okay, so you have the fan out F is the number of neighbors. So maybe 3 or 4 or 5, whatever. Each node has a certain number of neighbors. It's called the fan out. And you will do a certain number of hops or time steps. You do T times, so that's called T. So you have 3 kind of numbers. You have the buffer B, you have the fan out F, and the hops T. Okay? Okay, so let's study that a little bit. So it's like a disease. Let's say I have n nodes, population, Belgians, 11 million Belgians, around that. And each Belgian knows some neighbors, knows a number of people, which is the fan out. Okay, and one of the Belgians wants to tell something, wants to make gossip. That's very important because we all know that Belgium runs on gossip. Laws are very hard to enforce in Belgium because it has too many governments. You know this, regions, communities, provinces, federal government, whatever. Too many governments. So you need to you need to do it. So gossip is the way. So if I'm a Belgian and I want to send information, and I send to my fan out, and it keeps going, How does that work? It could be like a disease, huh? If I'm contaminated, I'm sick, and I will contaminate all you guys, and then you will contaminate your friends, and so on. How many cycles do we need before everybody knows, or everybody's infected? This actually comes from a very old book called The Mathematical Theory of Infectious Disease and Its Applications. That's very interesting. It seems very profound by a guy named Bailey, 75. So what is this guy studying? Well, he's studying how the infection propagates. Okay? So there's two models we look at, which is infect forever and infect and die. Infect forever means once I'm infected, I will stay infected forever. I never get cured. I don't actually die, but I keep infecting people. And I have one infectious individual, so I'm sick, round one. And every round, I'm infecting F other people. Okay? And after R rounds, which is the same as the cycles, YR is the fraction of individuals that are infected. And in each round, every individual tries to contaminate F others. Okay? So this is the formula that Mr. Bailey here comes up with. It's 1 over 1 plus n times e to the minus fr. So at the beginning, round 0, the total beginning, this is 1. You have 1 over n plus 1. So you only have one person infected. And then each round, you get more and more. So this is a negative exponential. So eventually, this number goes to 0. E to the minus fr gets very, very, very small. And n times this will converge to 0. And so this will converge to 1. So you have some number. It starts with 1 over n plus 1. And it eventually goes to 1. Okay, after a certain number of rounds. And after every round, the number of infected individuals increases by e to the f until you saturate. Eventually you get to almost everybody's infected, and then the two infected people will try to infect the same person. So it increases exponentially, but it turns into an S curve. So this is an S curve. So gossip can do that. So how long does it take to infect everybody? You can compute that. The number of rounds to infect the entire system is log to the base f plus 1 of n. So it's logarithmic. So it's logarithmic to the size. That's reasonable, because each round you multiply by something. If you have f is equal to 2, then round 1, you have one node. Beginning, let's say. Well, that's what you mean. It's nice to make a little picture to get intuition. So you start with one node. So if f is equal to 2, then this one node will infect two others after one round. And then after the next round, each of these nodes will infect two others. So you get this. Okay? So at round 3, you will get 9. And then if you keep going, it's like this. You multiply by 3 again, which is the little thing. And you keep going. So again, you multiply by 3. So this is then it will be 27, and so on. And if you do the computation, you see it's basically this. There's also some other factors, 1 over f log n. But it's basically log to the base f plus 1 of n. That means that a gossip algorithm takes logarithmic time to diffuse everything. That's very fast, though. It's not constant, but logarithmic. Okay. Now let me go to another model which is called infect and die. In this one, this is more like real diseases, diseases that we see. Every process will communicate the message exactly once. Okay? And that, after that, no further action is taken, even if copies of the same message are received again. So the process becomes immune. This is more like COVID, where I'm infectious, I infect a bunch of other people, then I get better again, and I cannot get the disease again, unless it's a variant, or not the same variant, but the infection keeps traveling. This is called infect and die. In this case, the computation is a little bit more complicated, because you have the number of processes contaminated, okay, is some kind of a fixed point computation, okay? Because eventually there's going to be lots of messages that were already contaminated, they will not propagate anymore, so everything stops. Whereas in the previous case, it keeps going, okay? So in the infect and die model, there's this equation, so you can compute the proportion of processes eventually contaminated, and this is actually a fixed point equation because we have two effects. The more that get contaminated, all these contaminated ones will get cured and they will prevent others from getting contaminated. So eventually there's kind of a stable situation. And if you compute it, it's like this. So pi is equal to 1 minus e to the minus pi f, and you have to solve this equation. Now, if f is equal to 1, then the fan out is 1. Okay, then I'm sick, but only one other person gets sick. And then one other person gets sick. So there's always only one person, which is 1 over n, which is like 0. Okay, so if f equals 1, then it's basically 0. But when f is greater than 1, you have some kind of a stable situation. Okay? When f is greater than 1, pi is positive. And if f gets bigger and bigger, pi gets closer to 1. So it's, there's sort of some kind of you can actually see this using a graph. So here I have pi, and here I have 1 minus e to the minus pi f. So that function is shown here, okay? And the intersection with the 45 degree, that's when it's equal to pi. So this intersection point is pi equal 1 minus e to the minus pi f. You can see when f is equal to 1, the intersection is here. But when f gets greater than 1, you have some kind of a bump. So it starts slow, but the higher that f gets, the more that it looks like this, and the more that this red intersection point approaches 1. Okay? So when f gets bigger and bigger, you have some stable equilibrium. So if you want this to be really close to 1, you need a big F. Okay? So effect and die is harder, and gossip is like halfway in between, Because when I do a disseminate, and I cannot keep the data forever. I can keep it a long time, but not forever. So it's not like I'm always going to be infectious. Okay? If you want to reach the whole system, which basically means there's maybe like only one node that you don't reach, so pi is very close to 1, then f, the fan out, has to be very high. But how high? Not that high. It has to be logarithmic. Okay. So it's actually you can actually have f logarithmic fan outs. Okay? And the number of rounds you can compute again, it's log n over log n. So log is a very interesting function because it's almost like a constant. Okay? It's not really constant, but it doesn't grow very fast. Okay? So it's basically, in practice, it's still like a log n. Okay? So that's the two models. We can see that there's a logarithmic effect. So that's very important. Now, there's lots of little tricky things that you have to arrange to make it work. Okay? So one trade-off is scalability versus reliability. What that means is how many neighbors. The more neighbors you have, the more reliable you are, but the less scalable. Okay? If I have a node here, I have a bunch of neighbors here, so this is a node Pi. These are neighbors. Okay? If the number of neighbors is log n, proportional to log n, already it's not so scalable. Because that means the storage, if Pi has to keep track of all these neighbors, it needs log n storage space. Okay? Or if the number of neighbors is square root of n, you need square root of n memory here. But it's more reliable. Because if some of the neighbors crash, I can keep going. If I only have 5 neighbors, then if all 5 of those crash, then it really breaks. Okay? Pi is out. But if I have log n neighbors, the probability of these guys breaking, all of them together, is extremely low, especially if they're randomly selected. So you have this trade-off, scalability versus reliability. Okay? Now you have other things. Network awareness and buffer management. The network awareness is how does this whole thing relate to the real network? I mean the physical network. You have random neighbors, but that's not really nice because you have the real network is on the Earth, so this is the Earth. So the nodes are somehow on the Earth here, connected, and these two nodes are very close. So here I have some abstract topology, and it's kind of like this. But these two nodes are actually very far away on the Earth. But in the network, I don't see that. Okay? It's just topology. I have 3 neighbors. But these two are very close, and this one is far. These two might be 10 kilometers, and this one might be 10,000 kilometers. So this goes against the randomness. It's actually a good idea to kind of follow the real topology. So there's some trade-off here, which I just mentioned here, called network awareness. Maybe you want to use hierarchy. So hierarchy means you have some kind of a tree here, and then you have connections between some other tree. Okay, that's the second thing. Third thing, buffer management. Well, if I do a lot of broadcasts, my buffer will fill up. What happens? Well, I have to drop some messages, okay? Low priority maybe, or old ones, or ones that they don't need, subsumed ones. So there's something I have to do here. And so it goes kind of halfway in between. Infect forever, where it stays forever, and infect and die, infect and die. And there's also a one where I become infectious again. Maybe I forget everything. Okay? So those are all important things. And there's some more information. Here I just want to say on membership, so each node knows a few. This is called partial view. And there is churn. Churn is a technical concept. That means the set of nodes is always changing. It's a function of time. But the number of nodes can be constant. Okay? If I have 1,000 nodes, 10 nodes fail, but 10 nodes come in. So the number stays about approximately constant. only varying very slowly. If people are looking at videos, the number will increase in the evening. When people go home and look at videos, it will decrease in the middle of the night or something. But the change in time is slow. Okay? So that's a point. So, membership protocols. Okay? Now, there's a lot of choices here, a lot of parameters, T and F, for example. How do nodes enter and leave? Do I have a website, a fixed set of nodes? And so there's a bunch of protocols here that I'm not going to explain. The Cyclone is in the project. So people designed protocols for this, and these protocols, they have names. So Cyclone, Newscast, Scamp are kind of well-known protocols that have been used in real systems, okay, to handle things. Okay. Broadcast buffer management, I'm not going to say so much of that. Maybe the old messages, so you have the age of the messages. Maybe the old ones are not important. Or maybe messages can get subsumed. Maybe you can merge messages. It all depends on the application. Okay, so that's all for the disease thing. Infect forever and infect and die. So you can see it's logarithmic, but there's a lot of things you can tweak. Okay? Now, I want to talk about a couple of things. One thing that's very important for gossip is what's called a small world network, because the gossip algorithm will run on a real world network, on internet, for example, or on a web graph, or as part of a social network. It will run on a real world network. And real world networks, the ones you find in the real world, are actually very special. And they're called small world networks. Okay? And it really affects how do you choose your neighbors, infection targets. How does a node choose its neighbor? So who are they connected to? Now, there's many ways that nodes can be connected. You have what's called a node graph. And you might think that the nodes are random. Maybe the nodes are randomly connected. Or maybe it's nearest neighbor. That nodes tend to be connected to the neighbors that are close by, but not to the faraway ones. Okay? So these are two kind of standard graphs. But what you see in the real world is not that. What you see is a really funny kind of in-between thing called small world networks. So that's something that the gossip algorithm will see. And what is a small world network? It was actually only discovered fairly recently. A small world network is a special kind of random graph. And I'll define it in a minute. And most real world networks, actually social networks, but any kind of a network in the real world is going to be a funny kind of graph called small world network. It won't be a regular random network where every node picks randomly a node. It won't be nearest neighbor where the nodes only pick the neighbors that are nodes that are close by. If I have a d-dimensional grid like a cube, every node has d neighbors. Okay, so you need 1 over d n to the power 1 over d rounds to propagate. But in a random network, this is what we saw before. The infect thing we saw before, the networks are random. Infect forever, infect and die. But real world networks are not like this. Real world networks are called small world networks, and they're very different. How are they different? Well, I'll explain it to you. And there's actually a course, LINFO2345 Reasoning about Highly Connected World, that studies all the effects of real world networks. Not just gossip, but all the effects when you have people, and it's using economics, and it's using game theory, how do people do economics on real world networks. And the networks are actually small world. So what is a small world network? Okay, a small world network is not random, it's not nearest neighbor. So a random network, every node picks a random node to connect to. Nearest neighbor, a node will only connect to close by nodes. But real world networks are not like this. It has both short and far away connections. It has nearest neighbor and long range. And the funny thing is that all nodes are close by. They can be reached with a small number of hops. Okay? Social networks, but also things like movie casts. So there's something called the Bacon number. I don't know if you ever heard of that. If you take two actors, if they play in the same movie, the Bacon number is 0. If they play in, if actor number 1 plays with another actor, and actor number 2 has played with that actor, then there's one movie in between, so the Ken Bacon number is 1. And so depending on how many steps in between, how many actors you have to go to get from one to the other. And it's based on Kevin Bacon because he has played in lots of movies, so many people have very small Bacon number. But it turns out almost all actors are very, very close to Kevin Bacon. That's weird. So the graph of movie actors, where there's a link between two actors when they play in the same movie, it's not a random graph, okay? Most nodes can be reached with a small number of hops, okay? So we make a formal definition now of this, of small world. It's a graph. So a small neural network has a small shortest path length. That means between any two nodes, there's a very short path, and it has a high clustering coefficient. That means the nodes are highly grouped together. That kind of seems contradictory, huh? So if you pick any two random nodes in this graph, there is a short path between them. But if the nodes tend to be highly bunched together, grouped, that means two nodes that are neighbors with a third node, they tend to be all neighbors, okay? So a small average shortest path length and a high clustering coefficient. So this is not like a random graph. A random graph, everything is very spread out, so the nodes are not clustered, okay? And a neighbor graph have a large distance, because if you only talk to people through their neighbors, if they're living far away, you have to go through a lot of neighbors. So neighbor graphs have a large distance between nodes, and random graphs are low clustered. So we actually have the opposite here. We have short distance and very clustered. Okay? And it's defined using something called the clustering coefficient. So the clustering, you define it. So these two numbers, so you have two properties. The average shortest path, and you have the clustering coefficient, okay? So the average shortest path, if I take two nodes and I make a path between them in the graph, but there's maybe many paths. So out of all the paths, I take the shortest. I take which one is the shortest. So maybe there's a path that goes it's very short, only 1, 2, 3, 4, 5 links. Okay, so that's the distance is 5. so the shortest path, the clustering coefficient, okay, if I have nodes that are neighbors, so for each node, I count the number of edges between neighboring nodes. So I look at this node, it has some neighbors, okay, so these are all neighbors. So this node N has neighbors. These are all neighbors. But how many of the neighbors are also connected? Maybe these two neighbors are connected. This one is connected to this one, like this, okay? So the neighbors are maybe also connected amongst themselves. So if I have, let me call this node P. If I have N neighbors, how many possible connections are there? So let me make a simple example. If I have a node P here that has 4 neighbors, the possible connections between them are 1, 2, 3, 4, 5, 6. These two, this one can also be connected. So these two, these are connected, these are connected, these two are connected, these two are connected. So that makes 6 possible connections. Sorry, I did this one twice. So if I have A, B, C, D, the connections are A, B, A, C, A, D, B, C, and B, D. Okay? And C, D. So that makes 6. So that is actually combinatorics. It's the number 4, choose 2. The number of a connection is 2. You should take 2 of these out of 4. Some people also write it like this. The combinations of 4 elements taken 2 by 2. So that's the maximum. So the clustering coefficient is how many of those that you have. So if all of these nodes are connected, the clustering coefficient will be equal to 6 divided by 4 choose 2, which is 1. Okay? If none of them are connected, it'll be 0. And depending on how many of the neighbors are connected, it will be some number between 0 and 1. Okay? Now, if you have high clustering coefficient, it means that all the nodes are actually very close together. So how can you have nodes that are close together and short path? So that was a big mystery until 1998. So 2 guys named Watts and Strogatz, they showed how you can do that. So here's a model. Here on the left is nearest neighbor graph. So each node has neighbors. 1, 2, 3, 4. So each node has just 4 neighbors on the ring. Okay? And here on the right, you have a pure random graph. Each node is connected to any other node randomly. Okay? And in the middle, you have a small world graph where the nodes, you have neighbors, but you also have long connections. Okay? So you can see on the nearest neighbor graph on the left, the distance is high when you go around. The clustering coefficient also is high. The nodes are clumped together. In the random graph, the distance is low. The nodes are all very close together. But they're also very dispersed. The clustering is low. And in the graph in the middle, you have low distance and high clustering. So it like takes the low distance of the random graph and takes the high clustering from the nearest neighbor. So this is a very special kind of graph. It's clumped together, but still you can reach anybody, even very far away. That's kind of very weird. And people didn't understand that until in the late 90s, when he said, look, yeah, actually real-world graphs are like that. They are doing this. They're not nearest neighbor, they're not random, there's something in the middle. Okay? And this is related to something called 6 degrees of freedom. So this is a famous experiment. This was from 1963. You know that people say that two random people, there's 6 connections between them. So for example, 6 is like a magic number. Between any 2 people on Earth, if 2 people know each other, that's a connection. And then the second person knows someone else, and so on. But between any 2 random people, you can find a chain of 6, maximum 6. So why is that? So the length is, so the distance is very small. That means between you guys and Barack Obama or Vladimir Putin, the link, the connection, the chain is very, very short. So how can that be? How can it be very short? Well, actually, it's possible because of the long-range links. So, for example, I know, and I've shaken hands with Vincent Blondel, who's the rector of the university. He has certainly met the Prime Minister of Belgium. This Prime Minister has probably met somebody who met Vladimir Putin. So between me and Putin, it's only 4 links. Not much, or maybe less, who knows. So here's an experiment. This would experiment show that. You forward letters, okay? So you have, on one side of the United States, you say, here's letters. Please, I want you to forward these letters to someone else. To someone you don't know. But the idea is, I get a letter, and there's a name on there. I send it to someone who I think is closer to that person. So for example, if I'm in New York, and I get a letter, and maybe that person is in California, well, that's easy. I know someone in California, so I send it to that person, and so on. And eventually the letter actually makes it to the destination. And the number of intermediaries is actually very small. So you can see 6 is like the maximum, the median pathway. So the length is very small, okay? And this is called a small world network. Okay, I actually am way over the break. Let's make a break now. So we saw small world networks. Here's an example of a small world, or real small world network. So they can be much bigger. This is some social network, and maybe it's not so easy to see, but you have a lot of clustering here. So the clumps, but also you have links that are going far away. High clustering together with short paths between nodes. And that actually helps, that's actually favorable for gossip algorithms. It means the gossip algorithm can cover a lot of nodes in very short number of paths, okay? So this is how real social networks look like. And nobody designed them like that. It's just the way the world works is like that. Your network of friends is like that. You have a bunch of friends, and your friends, they know each other, usually. But you also have some friends that are very far away. So you have short links and far links. So the short path, the 6 degrees of freedom, and clustering, okay? So that actually is favorable for gossip. That's a property of the real world. Okay, now let me now go to build gossip algorithms. Let me show you a famous kind of approach called the framework of Gelacity and Babao. So they invented a kind of general way of making gossip algorithms, and I'll show you how it works. It's very easy. So this is the code. This is the whole code of it. And so this code runs on every node. So there's 2 threads running, and they're both doing loops. Okay? There's the active thread and the passive thread. And so the active thread, it will wait. some time, amount of time. So this is the period, 50 milliseconds. It will pick a peer, so there's a function called select peer. It will send S, which is its local state, to Q, to this peer, and then it will wait for a response. It will pull the state of SQ from Q. So it sends its own state, it gets the answer, and then it uses S and SQ to update its own state. See how it works? Sends its own state to a random peer, it gets the value back, and then updates locally. And the passive thread is on the other side, so this guy is always waiting for this message. So it's waiting for somebody, P, to send it its state. So this is P and this is Q on another node. So this was like a wait. When someone picks this peer, sends it a message, P and SP will arrive. Then it sends its own state, S, back. So this S is actually the SQ coming in here. And then it also updates. So basically, you have two peers, each of them has its own state. This one sends its state there, this one sends its state back, and then they each they update their states. Okay? So this is a general framework. All you have to do is fill in the select peer and update functions. Okay? So that's how it works. Okay? You just have to instantiate it. So you define what is the local state? What is it? Is it a vector of things? Is it a number? You define the select peer method, and you define the update. And there's basically three ways you interact. So this is the general way, which is called push-pull, which means information goes both directions, but maybe the information only goes one way. So the push, that means no information is coming back, it's only going out. And the pull, it means no information goes out. I just send a message to a peer and it sends information back to me. So I'm asking for information. Okay? So the push is the active thread pushing information. Pull is the active thread asking for information, going in. And push-pull, it goes both ways. So those are the three ways you can do it. So that's it. And the rest is just how do you define select peer and update. And let me just give you one example, kind of a neat example, is how you can do kind of computation with this, which is aggregation. Okay? So you want to define some global number, okay? The maximum number of users on any node. So you have lots of computers. Maybe it's Apple who wants to get statistics on Mac OS, and without asking your advice, they're getting information from all the instances of Mac OS running. So this is an example of a pull algorithm, okay? And they can even be talking to each other to reduce the load, combining it. Some aggregate, they just need some aggregate, okay? So here's how it converges, and you can see, so this is an algorithm that computes some average number, and here is the number of cycles. So each cycle is like 50 milliseconds, but the nodes, each node does a back and forth, but they're not synchronized. So these cycles, they're not like synchronized. They can be a little bit offset from each other. It's approximate. It's not a problem. You can see that it starts out that the numbers are very, very bad. Okay? So you have some maximum and minimum value of the average. And this maximum minimum eventually converges. So you can see it starts out really bad, between 100,000 and some small number. Eventually it's converging, and after 15 cycles, they start getting already close to each other. And after 20 cycles, they get really close. And here, this part is like an expanded part of this from 22 to 30, where I'm expanding the vertical axis. So you can see it gets really, really close. It's like 3 digits precision after 28 cycles. So it's kind of neat. After 28 times 50 milliseconds, you can figure out some global number, okay? And there's a convergence rate, and you can compute what is going to be the convergence factor. The variance will decrease exponentially in the aggregates, and the convergence factor for this particular model is like 0.3. So the expansion of the variance squared is multiplied by 0.3. So after a few cycles, it gets very, very small, the variance. Huh? Okay? Now let me show you kind of a really interesting way of doing this, estimating how many nodes are in my system. This is totally unknown, okay? I have a whole bunch of nodes. Each node has neighbors. They're all running gossip. How many? Are there 1,000 or 10,000 or 5 million? Who knows? We can run a gossip algorithm. And the idea is very simple, but the trick is, how do you really make it work? So the idea is very good. We're going to make an averaging algorithm. If exactly one node has the value 1, and all the other nodes have value 0, if we make an average for all of them, it'll be 1 over n, right? And all we have to do is invert that, and we get the size. Ta-da! It's very clever, huh? Of course, the trick is, how do we make that simple idea really work in practice? For example, here I say, if exactly one node has value 1, how can we guarantee that exactly one node has value 1? Nobody knows all the nodes. We just have a whole bunch of nodes, and each node has some neighbors, and it's always changing. How can we guarantee that exactly one node has value 1? What do you think? Now I'm asking you guys something. You understand the idea, huh? So we have an algorithm that computes the global average of all the nodes. Basically, if you have 2 nodes with values p and q, then you replace those 2 by p plus q over 2 and p plus q over 2. And if you keep doing that, the whole system is going to converge, right? And it's not going to diverge, because the total value before is p plus q, and the value after the averaging step is p plus q over 2 plus p plus q over 2. It's also p plus q. So the averaging step does not change the total value. It just kind of smooths it out. Okay, you see how that works, huh? If I have a node with p and a node with q, then each one becomes p plus q over 2. And I keep running that, and eventually it all smooths out. Well, we hope, because if the nodes are really changing very fast, then maybe it won't smooth out so well. And in fact, we'll see it's not going to smooth out so well. But this only works if exactly one node has the value 1, and all others have the value 0. How do we arrange that? Yeah?
Can we have a network of n-1 nodes which agree on the value 0, and then we inject a separate node in?
They have to agree. So you want to make some agreement algorithm?
Maybe not some agreement.
How do you get them to agree?
They gossip the value 0, and then we inject a node which gossips the value 1, and then...
But you enter the value 0. How do you know when everybody has 0? But you have to use some trick. You can imagine that. It's not so simple, huh? You see, it works well, but you have to somehow arrange that exactly one node has value 1. And you can't really use agreement algorithm because there's too many nodes and they're always failing and it's always changing, huh? So you have to do something else. But you're on the right, kind of on the right track. So how do you do that? You can't do something like linear election. It doesn't work. Too many nodes, they're always changing. You have to use some trick. You have to use some kind of randomness is the trick. Okay? So here's the trick, if you want. Or what do you think? Maybe I give you a hint. So how can you make it so that maybe we don't need exactly one node to have one, but a very small number of nodes have one, for example. Or how can we have, when a node has one, and another node has one, that they don't interfere with each other? Let's say we pick one node with a 1. How can we make it so that it doesn't interfere with anyone else? How can we make that one special so that nobody else will have a 1? By using random numbers. Well, if we pick some random number, which is unique random number, and if it's big enough, number of bits is big enough, then nobody else is going to pick the same number up. The probability is very small. So if we pick a random number and then say that node has the value 1, and since nobody else knows the random number, they have value 0. And when we do the peer exchange, the random number gets filtered all over the place, and so it's like we get pairs of the average value and the unique identifier. So we do something like this. So here's an idea. I have a node here. I pick the number 1 and some unique ID. And nobody else will have it, because it's some random number. And then, so this one does not know it. And then we do the exchange. And after the exchange, this one will have 0 and a half, and it will have the unique ID. And this one will have 0 and a half and the unique ID. And then if we keep going, if we change with this one will be 0.25 unique ID. So you see what's happening? Is that the unique ID kind of guarantees that there's only one. Because nobody knows it, and when we keep doing gossip, eventually they'll learn about the unique ID, and then they will have some value. And then we keep going into the convergence. See how that works? Do you see what the idea?
So gossip is just a tuple.
So this is the state. So the state that you store locally is a tuple with the estimated average and some unique ID that you know nobody else will pick. And then you keep gossiping. Eventually everybody will have this tuple. And when I have two nodes that know the value, then they both have the U, then I just do the average. 375. 0.375, and then it keeps going. So the U kind of guarantees that you have this, that only one node has 1. Okay, so that kind of is reasonable, right? Do you see how that works? To really make it work, there's some probability. Every node doesn't do this, because otherwise you'd have too many of these unique IDs. There's some very low probability that a random node will generate this tuple and will start the algorithm. So you can have concurrent instances of this with different unique IDs. You have a node does 1.0 with a U1, and another node starts with 1.0 but has another value, U2. And then when they both talk to a third node, you actually have a vector or a list of both of these, U1 and U2. So you have like two separate worlds that are averaging, okay? And if the probability to start the concurrent instance is low enough, there won't be so many of them. Each concurrent instance is tagged with a unique identifier, and we can bound the number of instances. So maybe there's a maximum of 20 of these instances, and if we have more than 20, then we get rid of the oldest ones, for example. There's a timestamp or something. And we keep only the 20 recent ones or something, or we keep the 20 oldest ones. Maybe that's the best. So that actually works. And there's another trick that is used. If you do just this, then the convergence can be very slow, because the averages have to kind of propagate. So you periodically restart the algorithm. So you throw everything away except the values, the averages, and you start the algorithm again, okay? And you find the median values. So if I have an A1 and an A2, I find the median of all these guys. Maybe there's 20 of them. So that's kind of another trick to help it converge faster, okay? You take the median values from the previous epoch to start the new epoch, and then you run again the algorithm. And eventually the whole thing converges, and you know the network size. And this actually was run, and I show you some graphs of this. So here's the network size estimation. So here, the number of aggregation instances. So this is how many of these can you store in each node? 0, 5, 10. If you can store 20, it's better, of course. But it can't be unbounded. There's some limit. So maybe you store 30 maximum. Okay? And this is, in this network, we're going to make it a little bit harder. Each time you run the algorithm, at the beginning of each cycle, so every 50 milliseconds, you force 1,000 nodes to crash, and 1,000 new nodes come in to replace it, but they have no information, of course, these new nodes. And each data point, so there's always 100,000 nodes, but at the beginning of each cycle, you force 1,000 of them to crash. And each point here is converged, a converged point. So, for example, this point here is a converged. The algorithm runs until it converges when you have 10 aggregates. Okay? And then, after, when it converges, you take the median of those 10 and you throw away everything else and you restart the algorithm. Okay? And you converge to that. And you can see when the number of aggregates is very small, it's not that accurate. Okay? It goes from 95,000 to 110,000 or to 105,000. So there's like 10% error. Because of these crashes, we're kicking this algorithm. We're making it hard for this algorithm to get an answer. We're throwing away at the beginning of each cycle. Maybe the algorithm takes 20 cycles to converge, or 30 or 40. Well, that means 20,000 nodes will be replaced by new nodes. Fresh nodes that know nothing. You see how it's working? So we're seeing the algorithm work in kind of a hard situation. And you can see if the number of concurrent averages is 30 or 40, it's very narrow. So it's kind of pretty accurate, okay? It's a little bit less than 100,000 for some reason, but it's only like 1,000 this distance, okay? So it's like 1% accurate. It's not too bad, right? Of course, it's never going to be completely accurate, because you have all these nodes crashing. So you see this simple idea, you can actually make it work. See that? Neat, isn't it? So here's another measurement of network size estimation. Here again, you have the number of instances, so how many concurrent averaging computations you're doing, maximum. And here, whenever you send a message, there's a 20% chance it just disappears. 20% of the messages are lost. That's a very bad network, huh? So that makes things harder, of course, huh? That means when I try to do the round trip, sometimes nothing happens. You know, when I try to send, well, there's 20% chance nothing arrives or nothing gets back either. So a lot of these round trips are doing nothing. So that a lot less averaging is being done, and maybe information gets lost, okay? So this makes it worse. So you can see there's some kind of a fluctuation, but still it does better. But you can see it's not as good as the previous case. Look here, I'm going from 50,000 to 150,000. So here I still have some fluctuation. This might be how much? 20,000. Okay, so not so. So this is a very tough thing. Yeah? All messages, 20% chance that each message gets lost. And still I can kind of figure out there's 100,000 nodes in this system. Okay? So it actually works. No? What do you think of that? No? You can actually use gossip to figure out properties of very big, kind of messy, fluctuating networks. Huh? So gossip is like the last resort. Huh? When everything else breaks, the gossip will still work. Okay? So gossip is very important for internet algorithms. It's something that you don't see anywhere, but real internet systems like large cloud databases are using gossip to keep going. I mean, all the cloud databases are using anti-entropy protocols, which is a form of gossip, to fix errors, okay? So gossip is very important. Okay, let me give one final example. This is the more complicated one, so I'm not going to say everything today. This is topology management. This is when you try to lift, you have a bunch of random nodes and you try to lift them all and make some beautiful structure, okay? And you want, so you have a bunch of random nodes, but you want to organize them like a cube or in a ring or a torus, okay? And I'm going to show you, there's an algorithm called TMAN, topology management, and there's actually a paper on that, which is in the Moodle, so you can read, everything's explained. And this algorithm does something very sophisticated. It builds a beautiful ordered structure out of random set of nodes, okay? And many big internet systems are using this. So things like some implementations of BitTorrent or content distribution, they use these distributed hash tables, these overlay networks. They use these very complicated structures. And they use a gossip algorithm to build it, okay? So gossip actually is very useful for large distributed systems, okay? I'm not going to show you the whole thing. Let me just show you one thing, and then we'll be done for today. So you have a bunch of random nodes. Each node knows a few random neighbors. So it's a mess. It's like a random graph, or a small world network, which is still a kind of random graph. But I want a beautiful structure. So this is a torus. So a torus is like each node has 4 neighbors, and you can route this way and this way. So it's like a square in which you connect the opposite sides. So this is what I want. So here I have a node, and then I can go 4 ways to the 4 other nodes, and the nodes on the edges, I connect them to the other side. Okay? Like that. And also like this, on the top and the bottom. So this turns into, if you make a drawing of this, you have a square sheet. You first make it into a tube, like this. And then you connect the 2 parts of the tube together, so it kind of looks like a torus. So I'm not a very good artist. Sort of looks like that, tube. And it has this beautiful structure on it, where you can route. You can do routing on this, using something like Manhattan protocol. So I want to create this, but all I have is random nodes. I have each node knows a few random nodes, and that's it. Okay? Well, T-Man lets me do it, and it slowly converges. After 3 cycles, this is what it looks like. So it's still kind of messy now. In 0 cycles, there's nothing, of course. After 5 cycles, you can see it's starting to look like a torus, and after 15 cycles, it's a perfect torus. So this is an example with 2,500 nodes, and it builds them into this 50 by 50 torus. Okay? And so T-Man can let you do that. And it's not just that. If nodes crash here, if there's some kind of churn, if there's perturbation, I'm kicking this thing, the gossip algorithm will repair it, okay? It will keep fixing it if I try to break this. So I can actually do routing on this, whereas in the original random mess, I can't do routing. The nodes, they don't know each other. If I want to go from one node to some other node, I don't know how to do it. It's some random, they're just randomly connected. But at the end, I can actually route on this by following the links upwards or to the right. Okay? So you create order out of randomness. That's pretty amazing, huh? So gossip is like the ultimate bootstrap approach. And it's the most robust way of creating order out of randomness, but it's, of course, slow. The main disadvantage is that it's kind of slow, but it's very, very robust. Okay? Okay, so I will not show you the details of this, but I'll show you that next week. So let me stop here for today.